are about to learn about a unique and little-known industrial process that contributes greatly to our way of life. The members of the Metal Treating Institute present this to acquaint you with the basics of their trade, heat treating. Simply defined, heat treating prepares metals and parts made from metal for use. Any part, when first manufactured, may appear to be ready for use, but until it has been heat treated, it does not have the qualities that will make it perform satisfactorily. By blending the three essential elements of temperature, time, and technique, the world's heat treaters are able to transform metal and make them perform to their ultimate in today's high-technology world. One form of heat treatment makes parts stronger and more dependable, such as the sucker rods attached to the arm of this oil field jack pump. They must continuously perform their vital function hundreds and even thousands of feet in the ground. Yet another type of heat treatment produces extra hardness and metal cutting qualities as are necessary in a high-speed steel drill bit. And still a different process is used to develop softness and flexibility in metals so they can be bent or formed, as in this banding operation. As you see, many remarkable and essential characteristics can be added to metals simply by putting them through a heat treating process. Without this ability to modify the metal's character, very few tools, machines, appliances, or other mechanisms containing metal would be able to perform as we expect to. Of course, there are many metal-working processes that give metal products their specific shape, but only heat treating can enhance the metal and make the part truly functional. Let's take a moment and look more closely at the relationship between metalworking and heat treating. Forming and stamping processes have given this handsaw its outward shape and appearance, but only through heat treating can it obtain the cutting-edge hardness and spring-like qualities it needs to perform and hold up during repeated use. Forging and machining are the manufacturing processes that produced the drive and idler gears used on this crawler tractor. Heat treating imparts their strength and toughness, plus makes the gear teeth wear resistant. Wire sizing and roll forming are processes that create the springs in a rail car. Heat treating gives the spring both its rigidity and also its ability to spring. Here, a plant metallurgist working in a heat treating lab is performing a wide variety of test procedures associated with the processing of alloy steels. In order for you to fully understand the relationship between metalworking and heat treating, it is essential that you have a good working knowledge of the alloy steels used and the reasons why they are used. As you probably know, there is no one universal alloy composition that is usable for all metal parts. Consequently, as you begin the heat treat learning process, it is recommended that you first obtain some knowledge about the variety of metals that you'll be working with and the chemical composition of each of them. One of the basic ways of observing the various chemical elements present in a piece of alloy steel is a technique called spark testing. This procedure is used by many experienced heat treaters before processing to quickly validate the approximate chemical composition of a material before processing. Spark testing is conducted by bringing the steel to be tested against a high-speed abrasive wheel and then observing the sparks given off. The color, shape, and length of spark, as well as the burst pattern, are characteristics used to help determine the type of material. For illustration purposes, this high carbon material will give off a large number of star-like bursts. As the carbon content of a material decreases, the number of these carbon-bearing starbursts will also decrease. Many other chemical elements contained in steel have certain characteristics that can be observed and evaluated through spark testing. it is possible for experienced bark testers to determine within fairly close limits the alloys present and their approximate percentage. This is particularly true when a known chemistry sample is used to compare against. Most steel manufacturers have developed instructional handbooks that provide material chemistry and recommended temperatures for processing of their materials. The American Iron and Steel Institute, the Society of Automotive Engineers, and many other technical organizations have also published similar type information. To understand what's happening to the structure of steel during heat treatment, you might review a simple iron-carbon diagram and study temperature time charts and hardenability curves that apply to various alloy steels. At first, they may appear complicated, but with study, they become much easier to understand. And to learn about the various structural changes that occur in steels at various temperatures, consult a basic guide such as this one prepared by the Temple Division of Big 3 Industries. This chart explains the relationship of temperature to time in a wide variety of heat treating processes. It is advisable to build a personal reference log on the materials and their processing procedures. Your notes will prove helpful when you have the opportunity to perform the required heat treat processes. A wise philosopher once said, "You don't know how much you know until you know how little you know." Consequently, should you desire to further your knowledge of basic heat treating, you should consider obtaining and studying one or more of the publications available through the Metal Treating Institute. While there are many heat treating processes and a variety of techniques used to perform each of them, the four most widely used processes are hardening, tempering, annealing, and case hardening. Let's review each of them. Hardening is the most frequently used and normally consists of the following steps: heating, soaking, and quenching. The heating step is accomplished by loading the work to be hardened into a suitable environment that is already at the required hardening temperature, and then bringing the work to that temperature. This temperature is called the austenitizing or hardening temperature. Some of the more common types of equipment in use today for hardening are the open-fired furnace, the atmosphere-controlled integral quench furnace, as well as the molten salt bath and a fluidized bed furnace. The exact medium used for heating will vary depending upon the grade of material being processed, the geometry of the part, the end properties desired, and the experience of the heat treater. The actual temperatures used for hardening alloy steels will range from a low of approximately 1450 degrees Fahrenheit for water hardening tool steel to a high of around 2350 degrees Fahrenheit for high-speed tool steels. To avoid breakage, preheating before hardening is essential when tools such as these high-speed steel drill bits are to be hardened at a temperature of approximately 2200 degrees Fahrenheit. As shown in this remarkable sequence taken with special microphotographic equipment at the General Motors Research Laboratory, you can observe the internal structural changes that occur in steel during a typical hardening cycle. As the temperature is gradually increased to its proper hardening temperature, the chemical elements are capable of dissolving and holding the steel's alloys in solution in a much greater abundance. At elevated temperatures above approximately 1330 degrees Fahrenheit, the grain boundaries in the steel change when the atoms from one grain move across their own boundary and attach themselves to another grain. Thus, grain growth results with one grain growing at the expense of another grain. Soaking, or remaining at the prescribed hardening temperature, is often required to ensure that all alloys contained in the material are in the proper solution and the transformation to austenite is maximized. When using straight carbon steels, no soak is necessary provided the work has been heated slowly enough to allow complete uniformity of temperature. However, alloy steels, as shown here, are slow in reaching this solubility process, and a longer soaking time at temperature is necessary. When the alloys are fully dissolved, the resulting metallurgical structure is called austenite. While time does not allow us to provide you with an in-depth explanation of such items as heating and combustion systems, temperature and atmosphere controls, and the variety of atmospheres used in hardening, we think it will prove helpful to acquaint you with some of the processing equipment. Heat treating equipment, while varying from plant to plant, can be grouped into either the continuous category or the batch category. Batch describes equipment used for processing one single lot or batch of work that is loaded and also unloaded through the same opening after completion of the heating cycle. An example of batch equipment is the cylindrically shaped homo or pit furnace. In this type of equipment, work to be processed is loaded into a basket or racked on a fixture, and then is transferred to the heating chamber through a top opening lid or door for the required heating cycle. Upon removal from the heating chamber, the batch load is then quenched in a suitable cooling medium. Probably one of the more common types of batch equipment is the radiant tubed integral quench furnace. This furnace is a controlled atmosphere type and has a quench tank incorporated as an integral part of the equipment so that work can be transferred from the furnace to the quench tank without coming out into the air. Operation of an integral quench furnace can be practically automatic through the use of timers and other controls, requiring only that the work container be manually loaded into the furnace at the start of the processing cycle and transferred to the vestibule elevator for quenching at the end of the cycle. This equipment is generally used to process batches of work that can be loaded or fixtured in processing containers as shown here. Still, other examples of batch equipment include both high and low temperature molten salt baths and induction and flame heating, which use specially designed electrical coils or gas burner heads to apply heat selectively to the parts before they are quenched. The second category of equipment is the continuous furnace line used for heat treating large quantities of identical parts. In this type of equipment, the parts to be processed are continuously fed or hand-loaded into the charge end of the line and are individually carried through a variety of uniform heating, soaking, quenching, washing, and tempering cycles by some type of conveyor mechanism and then discharged at the opposite end of the line. The design shown here illustrates the alloy belt method used for advancing work through a furnace. Another type, called the shaker hearth, uses an alloy pan or trough to contain the work. Work is advanced along the length of the pan encased in a hot retort by applying a bumping, vibrating, or shaking action to one end of the pan at predetermined intervals. The last step in the complex hardening process is known as quenching and is basically the cooling down of steels in an appropriate cooling medium. Typical quenchants include plain water, caustic and water solutions, oils, molten salt at various temperatures, and a multitude of atmosphere gases, including air. It should be pointed out that it is of vital importance to choose the proper quenching medium for the grade of steel being processed. It is likewise important to make sure that the flow of quenching solution is cooling the parts uniformly. The lower the alloy content of steel, the faster it must be quenched in order to obtain maximum hardness. For instance, low-carbon steels like these have to be cooled rapidly in the proper quenching solution, while highly alloyed materials should be cooled at a much slower rate in oil or some other less drastic quench solution. Most heat treaters agree that the slowest possible quenching rate that will develop full hardness is the best one to use. Tempering. After steel has been properly heated and quenched to obtain maximum hardness, it is highly stressed and is too brittle to be of practical use. To eliminate this condition, the steel must be reheated at a temperature lower than that used for hardening. Then reduce the brittleness and make the material usable. In most steels, the higher the reheating temperature, the greater the loss in hardness, but with an offsetting increase in toughness. Another factor that must be observed when tempering is to allow plenty of time for the material to soak at the required temperature. The time will vary depending upon the mass or cross-section of the part and the grade of the material. A good rule of thumb used by many heat treaters for tempering is to soak work at the tempering temperature for a minimum of 1 hour for each inch of cross-section. Technically, this operation is called tempering, but in common shop language, it is also called drawing, which comes from the concept of drawing back the hardness. The temperatures used for drawing range from 300 degrees Fahrenheit to approximately 1200 degrees Fahrenheit and must be held within very close limits if the optimum hardness and toughness are to be obtained. Annealing is a broad term used to describe a variety of heat treating processes that require heating a particular analysis of material to a predetermined temperature, holding it at that temperature for a suitable time, and then cooling it at an appropriate rate to accomplish a desired objective. While there are many annealing processes, the following are the most often used. Full anneal is a process that requires the metal to be heated to a particular temperature and then slowly cooled, usually in the furnace, back to room temperature. Full annealing is used to soften steel and to relieve internal stresses caused by casting, forging, or a previous heat treatment. Normalize differs from a full anneal only in the rate of cooling. After being heated to a high temperature, work is removed from the furnace and then cooled down to room temperature in still air. The primary purpose of this process is to refine the grain structure before hardening. SPHEROIDIZE anneal is a term applied to a lengthy heating, soaking, and cooling process that produces a rounded or spheroidal form of iron carbide in the steel structure. Spheroidizing is normally used on carbon steels, such as contained in these wire coils, to improve machinability or cold workability. Stress relieving is a relatively simple process that normally requires heating the parts to a temperature of approximately 1200 to 1300 degrees Fahrenheit and then removing it from the furnace and allowing it to air cool. Stress relieving is primarily used to relieve stresses caused by machining, welding, stamping, or forming. The fourth major category of heat treating processes is identified as case hardening. These processes add carbon, nitrogen, or both to the surface of the steel, while the part's interior, or core, retains the properties of the original material. Case hardening processes are usually performed to provide a more wear-resistant surface. Three of the major varieties of case hardening processes include carburizing, a case hardening process in which carbon is introduced into the surface layer of steel by heating the material to a temperature between 1500 degrees Fahrenheit and 1750 degrees Fahrenheit, while the metal is in contact with carbon-rich compounds, liquids, or gases. Carburizing is normally used to provide a case depth of up to approximately 1/100,000th of an inch. Carbonitriding is a process in which carbon and nitrogen are added to the surface of steel from a gas atmosphere rich in both elements. Carbonitriding normally is used for case depths up to 20,000ths of an inch and is usually performed at temperatures between 1450 degrees Fahrenheit and 1550 degrees Fahrenheit. Nitriding is another case hardening process that is performed by loading certain alloy steels that are suitable for the nitriding process into an airtight retort that is then heated to about 1,000 degrees Fahrenheit while exposed to an ammonia gas. The heat causes the ammonia to break down into nitrogen and hydrogen. The nitrogen combines with the iron in the steel to form a chemical compound in the outer layer called iron nitride. This layer gives the steel's surface a particularly hard and wear-resistant character. Modern heat treaters use a variety of process control and inspection procedures to ensure that maximum quality is consistently maintained throughout heat treat processing. As part of this learning experience, we would like to explain a few of them. The Rockwell hardness tester is probably the most common piece of equipment in use today for inspecting the hardness of alloy steels. This instrument measures steel hardness by the depth of penetration of the diamond braille or steel ball under a fixed load condition. Preparation of the material surface before testing is of major importance. It is essential to have parallel and clean surfaces on which to make a test, as the diamond must penetrate the material squarely in order to get a proper reading. After selecting the part to be inspected, it is elevated on an anvil and is brought into contact with the braille. The machine is zeroed out and the appropriate load weight is applied by tripping the handle. When the indicator comes to a stop, the hardness is read directly from the dial on the instrument. While there are several scales available on most Rockwell machines, the most frequently used is referred to as the C scale, and the higher the C scale number, the greater the hardness. In some cases, the exact depth of hardening must be determined. When required, this is accomplished by using a Tucon micro hardness tester. The section measured is cut, mounted in plastic, polished, and positioned on the machine. Then, through the use of a microscope and a micrometer table on which the section has been placed, the exact point that is desired to be checked for hardness is located. By using a specially shaped elongated diamond indenter, a very light load can be applied. The length of the impression is then measured using the microscope and converted to a hardness value. Again, the smaller the indentation, the harder the metal. Brinell hardness tests are made by forcing a steel ball into the surface of the material to be tested under a fixed load, and then measuring the diameter of the impression. Brinell equipment is most often used to check the hardness of castings and forgings. The diameter of the depression made in the material tested is measured in millimeters using a Brinell glass, and then converted to a hardness number indicated on an established table. A common method used to check case depth and steel structure quality is to cut a representative cross-section from a part. This specimen is then polished to a mirror-like finish on the surface to be inspected, followed by etching in a suitable solution to bring out the cased area. The sample is then measured with a Brinell glass, or if a more accurate measurement is required, it can be examined under a microscope. Oftentimes, a magnifying television-like screen is used to make viewing easier. Because of the continuing breakdown of quench oil during use, its ability to extract heat must be constantly monitored. This is accomplished by means of a hot wire test, which measures the amperage required to melt a wire that has been placed between two terminals and then submerged in a beaker of the oil being tested. The power is then gradually applied until the wire burns out. The oil's quenching speed varies directly with the amperage carried by the wire. Successful heat treatment requires that carefully controlled balances be maintained in heat-treating chemicals used in the various processes. The required chemical concentrations are determined by means of a process control known as titration. This method uses a measured quantity of a known substance to calculate what percentage of a second substance is present. As today's society continues to expand its horizons through new and ever-changing technology, the members of the Metal Treating Institute stand ready to meet the new challenges through the efficient management of temperature, time, and technique in their heat-treating operations. Whenever you see this symbol, it is a sign of a commercial heat treater who is a master craftsman.